Uh, Sorry about that. Yeah, let me share my screen once again. Okay, yeah. So the part two that is due on next week will cover this advanced um, areas, that is testing different standards, DFMEA, some real life examples, and this part two is going to be taught by Mr. Vivin. And Vivin has 13 years of experience, most of it in this cooling and fuel system. So you should get some good learning from him also. Okay. So yeah, let us start with the introduction part. So first, we need to know that what does cooling system do and why is it significant. Okay. Some of you who have read the IC engine, took the IC engine course, know about this stuff. Okay, but let me do this once again and add some a bit more detail from my personal experience. Okay, so more than 30% of energy in the engine is rejected in the form of heat, right? We all know this, but there are we need a mechanism to handle that heat, okay, to safely carry it away. But also cooling system serves several other functions. For example, we need to keep the cylinder wall temperature, okay, on a consistent limit. Too high the temperature, okay, or too low the temperature, it becomes difficult. So overcooling reduces the cylinder wall temperature, it reduces the engine efficiency because more amount of heat is being rejected. Another thing is with the low temperature cylinder, sometimes what it results in, difficulty in burning of the fuel that is adjacent to the cylinder wall. Okay. So this results in half burned or unburned fuel. Okay, that is a environmental hazard. Right? And undercooling results in like a lots of problem. Most of you know that undercooling will result in pre-ignition or knocking. Okay, sometimes oil will burn if the cooling is not sufficient, and in worst case scenarios engine might seize. Right? Okay, another purpose of the cooling system is to warm up the cold engine in cold days, cold countries. It is quintessential because at such low temperatures the engine could not start. And another purpose it serves is the cabin heating. Okay. So, in cold climates, especially, cabin heating is very important. Okay. Uh, okay. Next, moving on, I'm going to spend less time on these very basic things. Okay, you can go and search them on Google, and these are quite basic. So, little bit of advanced stuffs. If we have to get time for that, we have to skip the basic things. Okay. Another thing is, well, cooling system is very significant in this aspect that it actually classifies engines, right? Engine are classified based on cooling systems also. So as you can see in motorcycles, especially, you can see all these three kind of engines. Okay, air cooled, water cooled, and liquid cooled. Okay. So what is the difference? Air cooled, water cooled, and liquid cooled. So basically, what air cooled is, as it says, there is no separate cooling mechanism. The fins does the cooling. Okay, it is rejected through the fins only. The oil cooled thing is just an air cooled engine. Okay, in that engine, the lubricating oil is also being cooled. This is a like heat exchanger. Okay, it is cooling the oil. Sometimes heat exchanger will connect to a water radiator. Okay, a very small water radiator, and that radiator will cool this oil instead. And another is liquid cooled, and so the air cooled engines can only be used up to maybe 150 cc, sometimes 200 cc. Okay. The oil cooled engine maybe 300 400 cc. Okay. But above that we need a liquid cooled engine. The liquid cooled engine is like normal car engine with cooling jacket and water and all. Okay. So each have their own advantages, disadvantages. Liquid cool is the most effective, and but it is more heaviest also. So it goes the other way around. also. For example, air cooled is the lightest, but it's the least effective. Okay, and yeah, next what we see is the components and working principle. Please pay attention here. I don't have any fancy animation today to show the components and working principles. So please pay attention on the circuits. Take notes if necessary. Also, you will hear along with lots of other reference material. Bear in mind this area is quite a research focused area, so there will be lots of dissertations. So please download those after this class ends. And in order to download those, you have to fill up the feedback form. Okay, then after filling up the feedback form, you'll get a link to download. Link to the folder, Google Drive folder, and you can find all the documents there. Okay, so yeah, let's see a simple engine cooling system. Okay. It's the simplest type of schematic. If I use a pen, yeah. So yes, as you can see, this is our engine block. Okay, this is our engine block, and hot water is going out of this. How do I change color? Yeah. So hot water is going out of this and into the radiator. Right. From radiator, it is getting cooled and returning to the engine. Okay. So basically, focus on this only for right now. We'll add more complexity on this model. So this is the simplest model of a cooling system. Right. Now, there are other components also, as you can see. First of all, by common sense, we know that we need a pump. So in order to push this coolant, we need a pump. And then, as you can see, there is a oil cooler. Just a second, someone else was annotating. Let me just disable that.
What you need? Ah. Thank you.
Yeah. So yeah, from pump is there to drive the coolant. Can everyone please mute yourself? Has a wax-like material inside of it. Okay, and yeah, this wax materials allows the thermostat to expand or contract in terms of temperature. So when the engine is cooled, okay, when the engine is cold, the thermostat is open in this case. Okay, there are two types of configuration. One is thermostat open and thermostat closed when starting up. Okay, in this particular configuration, thermostat is maybe open. Okay, so what will happen is there is a bypass connection. It is not exactly shown here, okay. But yeah, there will be a connection from the outlet to the thermostat. Okay, and when the thermostat valve is open, the coolant will directly go to the uh, engine and circulate just here. It will not go to the radiator. Okay. and when the thermostat is closed, it will go via the radiator. Okay, so this is just a simple Y connector, but it has the ability to open and close depending upon the temperature of the circuit. Okay, there is another circuit, as you can see here, that is the heater circuit. Okay, so this one actually exists here. Okay, we have multiple temperature sensors. Okay, this simple model doesn't show all of them. Okay, but this what it does is basically there is a thing called heater core. It's non-existent in the cars that we see because we don't have cold climate, but in cold climates there is a heating mechanism, heating arrangement in the, or the cabin heating mechanism. So what it does is takes hot water from the coolant. Okay, uses that hot water to heat up cabin air. Okay. So this is the heater core. Okay, there are blowers and stuff to heat up the cabin air. Okay. Yeah, so this is was a very simple cooling circuit. So the thing to notice is this is the bare minimum. Okay, current engines will have a turbocharger. Okay, that's why it will have a intercooler. Okay, uh, the diesel engines sometimes it will have a EGR or a exhaust gas recirculation system. Okay. So normally it will be much more complex. Okay. So again, this is the simple cooling circuit that we just discussed. Okay. Mm, yeah, I'm not going to go through each component by component. Maybe that is a, oh, that will be a focus for another class. Today we are focusing on a system level design approach. Okay, but yeah, the same thing that I discussed here, you can see from here. The coolant from engine is coming to the radiator. Okay, and radiators, this is called the upper reservoir of the radiator. Okay. Then this coolant travels downwards. Okay, after traveling downwards, it goes to the lower reservoir, and from there, yeah, it is going back to the engine. Okay, on the way there is a thing called expansion tank. Okay, this connection might come from here also, it is more common, or the expansion tank, there is another connection, this one. Okay. Okay. So this is called the degas connection. What it does is when the coolant capacity exceeds the limit of the circuit, okay, the capacity of the circuit, the excess coolant or steam, anything will go here on the expansion tank. Okay. So if steam reaches the expansion tank, after coming here, it will condense and turn into water. Okay, and when the circuit cools down, okay, it will pull the coolant again. Okay, as you can see this arrow here, it shows the coolant is being pulled in this direction. Similarly, yeah, there is another line called this steam hose. Okay, this is the connection that is coming from the engine, because inside of the engine cooling jacket also steam is being generated due to uneven heating. There are some hot spots which are creating steams. Okay, so this, all of this steam is coming to this expansion tank, and that is why this tank is also called degas tank, because what it does is removes the gas and liquid. Okay, it separates them. So very important piece of component. People often overlook it, but in designing this, I find it very complex. Okay, because most of the other components are not designed by any OEM. For example, the radiator. All we have to do is do some calculation, pick a radiator from a catalog that the supplier has provided. In case that particular radiator is not available, then it becomes a lot of work to develop that radiator. But also, even then, 50% of work is done by the supplier. Okay, for this water pump. Okay, or maybe the thermostat, those are all bought out component, that is the ready-made component. We don't have to modify them. Okay, standard components. But yeah, this is something that we have to make from scratch. Okay, also another thing that we have to make from scratch is the cooling circuit itself. Okay, there are a lot of different ways to create this circuit. Okay, especially when there are different components to work with. Okay, but yeah, in case of a simple one engine, one radiator configuration, it's either one kind of thermostat or another, and sometimes these degas connections will change. Okay, as I was saying, showing on that schematic, there is this connection for the heater core. Okay, as you can see, uh, coolant is going through this direction from engine to the heater core. Okay, and returning from here. This is a blower. It is blowing air to the cabin. Okay, so through the little AC holes, the passengers are getting warm air. Yeah, let me show you a little bit complex circuit. Okay. So this one is a circuit of a turbocharged diesel engine. As you can see, this has a little bit more elements than the normal circuit. Just like the previous one, okay, this has the radiator circuit. Let me just take another color pen. Yeah. So as you can see, this exit to the radiator. Okay, pumps and all. Mm, Sorry. Yeah. Um, how do I- okay. So yeah, this is our engine. This is a pump, as you can tell from the symbol. Okay. So it's going to the radiator. Okay. There is also a bypass connection, and through the radiator is returning to the engine, just like the previous one. But there are also other things here. For example, it has a CAC. CAC means charge air cooler. It is also called intercooler. Okay. The job of the intercooler is to cool down the hot air that is coming from the turbocharger. As you can see, this is a turbocharger. Okay, this is the exhaust. Okay, that is going through the turbo, and this is the charger. Okay, so it is sucking in fresh air, but due to high compression this air is very hot, so we need to cool it down before sending it into the engine. So cooling this one is done by this CAC. Okay, charge air cooler. And in order to cool the water that is coming to the charge air cooler, so as you can see, the water is coming to the charge air cooler, right? Okay, and it is cooling down the charge air cooler and the air. So this in order to cool down this water, we have to use another radiator. Okay, now we are calling it low temperature radiator, so this one automatically becomes high temperature radiator, right? Previously it was just one radiator, now it is low temperature and high temperature radiator. So now essentially we have two cooling circuits. One is low temperature circuit, one is high temperature circuit. If we have a hybrid vehicle, okay, then also we will have a low temperature radiator. Maybe we'll have utilize this same radiator, okay, or add another low temperature radiator based upon the requirement. But any hybrid vehicle will have a low temperature and a high temperature radiator circuit. Okay, any electric vehicle will have only a low temperature circuit configuration. One funny thing to know is that in electric vehicle also radiators are not actually that much smaller. Those radiators are still huge because the temperature of the circuit in electric vehicle is very less. The coolant temperature is low, and that's why the effective heat transfer is less. So that's why we need a large radiator to transfer small amount of it because the temperature difference is low. Okay. Okay. Yeah. Now this one shows another connection to the cabin heater. Okay. Another thing that I have to show is this EGR system. Okay. EGR means exhaust gas recirculation. This is something that is unique to diesel engines only. Okay. So what it does is, as you can see, this is the exhaust. Okay, it doesn't say specifically, but this is the exhaust. Okay, so part of the exhaust is being recirculated back to the engine. Okay, this actually improves the efficiency. Okay, but on the expense of losing some power. But yeah, this is great for fuel efficiency and mileage. Okay. So we cannot just insert the burning hot gas inside the engine because it will result in pre-ignition. Okay, so what we have to do, cool it down first. Okay, there is some limit on how much to cool, but we need to cool it down. So what we are doing is, yeah, we are uh, having coolant, okay, go through this exhaust gas cooler, okay, or the AGR cooler, okay, and yeah, it will eventually go to the radiator. Okay. We also sometimes need cooling for the turbochargers. Some kind of turbochargers need cooling, and it will water will pass between their shells. Okay, at least in the turbo sides. Okay, cheaper turbos don't have cooling, and they sometimes becomes red hot. Okay, after running. So yeah, lots of elements are being added here. And another thing that is quintessential for a cooling system is the fan. Okay, we'll look into the design of fan and radiator. Okay, so please keep your handbooks ready. We are going to look at a lot of formulas, and you don't need to write down each and every formula because you'll get the presentation, but note down the key things, okay, because it's easy to forget these things. So next up, we are going to look at the concept level design of cooling system. So yeah, one thing I would like to repeat again, I am not going to go component by component basis on this one class. It's very difficult to go through all the components in one single class. If we really want to cover these things in depth, then I'll need 3 4 classes for radiator only. But yeah, we're going to look at the concept level design of cooling system, basically the architecture. Okay, how do we design the cooling system from scratch? Right now, we start from a blank piece of paper. Okay, so there are calculations. Okay, basically concept level design of cooling system means calculations. uh, or the entire cooling system can be like calculated on a piece of paper if you have sufficient amount of knowledge, and it will work. In older days, people used to do just like that. Right now we need very high precision because the margin is low. We have to cover cost and weight. These are very tight. That's why we need to do all kinds of test and analysis. But yeah, if our criteria is loose, then this hand calculation will do. Okay. So I have been doing this for quite some time. Four total projects I have completed still till now, and yeah, none of my engines actually exploded or seized. So yeah, I think pretty confident on this area. So there are six different elements to designing a cooling system on the concept level. First and the most important, the biggest perhaps, is the engine heat rejection. Okay. We have to calculate how much heat is being rejected. Okay. Uh, the 30% heat rejection, that's just a vague assumption. It doesn't work for all kinds of engine. So that's one thing we're going to look into. That the next is the radiator calculations. So another very large thing. So the purpose of radiator calculation for us is to um, is to yeah, choose a radiator from the catalog that is provided by the supplier. Most of the OEMs does it like that. But another purpose of the radiator calculation is that if uh, we get to check like which kind of situation we are dealing with. See, sometimes what happens is uh, from the body department maybe or the styling department will get a space like, yeah, Chayan, you have this much of area for the radiator. Okay, maybe it is 300 wide, or maybe 400 in height. Okay, very unlike normal car radiators, but in sports car radiators tend to be portrait shape. But yeah, that is the size that I have for a radiator. But my initial calculation shows that the that kind of size is not sufficient. Okay, In that case, we have to act on it quickly. If I wait for all the frozen data to calculate the radiator and find out which kind of radiator, what is the size that I need, it might be too late. If other people, other departments may have frozen their areas, and it will result in like millions of extra cost, not a few thousand or lakhs, millions, many crores. Okay, so yeah, the next one is fan calculation. Fan calculation is quite simple, easy. These days we don't even have to always perform it by hand, but it you should know this. Okay. Suppliers will have some kind of softwares. Some of the suppliers have online data entry options where you can enter your data or requirements. They'll give you suggestions. Okay. But you should always know how to calculate fan, because you cannot always trust the supplier judgment. Okay. You are the person who is responsible for the delivery. For example, me as a project engineer or just as a senior engineer, I am actually answerable for all of these things. Anything goes wrong, I cannot put show my finger to anybody else that yeah, it's that guy's fault. It will always be my responsibility. So I have to validate everything. The next is coolant pump creation calculation. Okay, so the pump calculation basically what we do is we calculate the pressure drop around the circuit. Okay, how much pressure is dropping, and based out of that we choose the right kind of pump. Okay, because we whatever the pressure drop is, the term pressure drop might confuse some of you, but yeah, as you can see, when the fluid travels through all the resistance, right, like the frictional resistance of the pipe, okay, or inside the radiator, okay, it has to go through small holes, okay, then large, then small, so there are losses. Okay, if you have already read fluid mechanics, okay, then there are chapters on losses, right? One is major losses, one is minor losses. So lots of losses are occurring, which results in pressure drop. Okay, so the amount of pressure drop that we experience, we have to compensate it with the pump. Okay, and the pump should also maintain a certain flow rate. Okay, then the next thing we need to know is the total coolant capacity. It's a small calculation, okay, but very hard to get it right just by calculating. So a lot of the time we end up doing tests, or at least virtual like CIE, CFD. And the last thing that we need to calculate is the capacity of the expansion tank. So let's get on with it. The engine heat rejection calculation first. Okay. So engine heat rejection models. There are different models of engine heat rejection. Okay. Depending upon how much data is available with us. Suppose we don't have any kind of data. Okay. Then we can simply assume that yeah, almost 30% of heat is going through the coolant. Okay. We don't even always have to assume that 30% is going through the coolant. We can look at our past programs or our benchmark vehicles. Okay, and sometimes we can even test them. Okay, you don't have to test it by yourself. You just have to send a request to the testing department or the benchmarking department that yeah, we need to test this car for and we need to find out how much heat is being rejected. Okay, and it can be done. Okay. So this is one method, the benchmarking method. Okay. Another method, if we have some amount of data, then what we use is Lavix empirical correlation. So this is a empirical correlation, like not a model based. Okay. So it is done based on the experiences, based on the data. Okay, this is not a mathematical solution. Okay, so this Lavix empirical correlation is fairly correct. In my opinion, it is like around 6-7%, up to 6-7%. Um, it gives a result that is almost 6 to 7%. If more data is available, then what we do is use the Parish's correlation. Okay, and this one is a model-based correlation. What it means is it's mathematically calculated. Okay, considering all the factors. So this one requires a lots of data to begin with. Okay, we are going to look at all of these models. Okay, and if we have the entire detailed engine data, for example, we have the model, we have the CAD model, we have some CAE CFD data, then we can go with the 3D CAE and CFD, okay, and followed by 1D simulation. Okay. What 1D simulation does is it saves lots of time, and we can do quick trials. Okay, we can do quick changes, setup changes, and we can see how it is effective. So if a 1D simulation takes maybe 30 minutes, okay, the same amount of work on an actual CFD will take on maybe on our system never, it will never end. On a very high end system it will take weeks. Okay? So it's not possible to wait for 1 week for a simple change. That's why we do 1D simulation. 1D simulation has some errors. Okay? That's why we need to calibrate them. We're going to discuss about that also. Okay, so first thing, we don't know anything, so we are assuming. So 30% of heat is lost to coolant. Okay, so as you can see here, as I was saying, these are some benchmark data. On the left hand side, you can see a curve showing heat rejected versus brake power. Okay, there are two curves for two kinds of engine. The top curve is for CNG engine, the bottom curve is for diesel engine. Okay, and the CNG engine has this, as you can see, it has more heat rejection, okay, per unit of brake horsepower, as you can see from this curve. Okay, so in terms of this, it is fairly inefficient. Okay, but the CNG engine saves on other areas. But as you can see, a diesel engine is giving rejecting heat. For example, if we take this example at around 2400 brake horsepower, okay, 2400 kilowatt, that is the brake horsepower. In this brake horsepower, we are rejecting almost 600 kilowatt of heat. So that means it is around 25%. Okay? So yeah, less than 30%. But in this case, for the same engines, we are also losing heat for from this aftercooler or the turbocharger. Okay? If we don't have turbocharger, as you can see, we have this 25% of efficiency. If we have a turbocharger, okay, for this 2400, we'll lose another 400, right? Okay, but this is a slightly misleading curve because not always these are not the same engines. Okay? Because if these same engines are having turbochargers, their efficiency here will improve. Okay. Another thing is that with the turbocharger, sometimes we have a loss of fuel efficiency, but with a gain in power. So that's a trade-off. But as you can see, this adds another 15%. So if this is one engine, one diesel engine, which is turbocharged engine, then it will lose around 40% of heat, okay, through coolant. So using this benchmark data, we can calculate, we can make a fairly good assumption of what kind of heat rejection we are looking at. Okay. So a quick note before start. After finishing this lesson, I request everyone, if you have any interest in this area, do not jump directly into all the like cooling system related design stuff. Okay, first come learn the basic. Okay, I think most of you have completed already the heat and mass transfer subject. Okay, what I request is to look at it once again. Okay, from a practical point of view. Okay, and for this I recommend this heat and mass transfer book by Senjal and Gajar. So a good book, focus on the convection part. Okay, the boundary separation and all this kind of stuff, very useful for calculating the heat transfer, especially around the radiator. Okay, so now the Labix empirical correlation. Okay, so this is the formula. I'm not going to go line by line on that formula, but as you can see, this is the function of the displacement of the engine, that is how many cc the engine is, right? The swept volume, and then we have our RPM, torque, and brake power, or the brake horsepower. So it's simply a factor of all of these four elements. So very simple relation. Okay. Just have to copy paste and put the values. Okay, so yeah, this is the Lavic empirical correlation. I have added lots of different reference material with this uh, presentation in that folder. Okay, all the research paper, dissertation. So you can download them by filling out the feedback form. Okay, so all of these are provided there. So the next one is model based correlation of Paris. So this is you can see quite a complex equation. Okay, and it considers all the things like the thermal conductivity, this kg. This is the thermal conductivity of the cylinder. Okay, let me go in sync with the PPT. Okay, so it considers the heat generated by friction. Okay, the friction between the piston and the cylinder. Okay, it considers the heat that is taken away by the charge that is inducted into the cylinder, right? So as you can see, this VD into N by 2, it's just charge per cycle, right? Mm, per unit time. And then correlation for the specific heat rejected to the coolant, for example here. So this is specific heat rejection, that means heat rejection per unit of uh, power generated. Okay, this any means power generated. So yeah, I did not change the default term. Okay, so any means the power generated. So as you can see, it considers radiation, because as you can see we have the Stephen Boltzmann's constant here. Okay, it considers the cylinder diameter. This way it calculates the mm, friction. Okay, we have kg pr. So kg, that is the thermal conductivity of the wall. Okay, and pr, we have the Prandtl number. Okay, whenever we have Prandtl number, we are considering the convection part. Okay, so it is considering the convection from the cylinder wall to the inside the jacket. Okay, inside the cooling jacket we have water, right? So Prandtl number shows that we are considering that also. Okay. The Renault number shows that we are considering the flow characteristics. Okay, in the cylinder. In the cylinder, that is how the gas is, the exhaust gas is flowing inside the cylinder. And then TGTF. Okay, these are the main the values of like the gas temperature. Okay, the temperature before burning. Okay, then we have the flame temperature. Once it burns, how much is it? Then we have our wall temperature. So it's considering a lot of thing in considerations. And yes, with these Parish's model, we can get a great deal of information from nothing. Okay, even if we have nothing, just these values, all of these values can be calculated, or at least like uh, you can get them from a chart. This kg pr Reynolds number, all of this you can get from a chart. This is a constant, right? Stephen Boltzmann. And diameter of the cylinder is a very basic value. Okay, so this flame temperature is mostly common for a particular type of fuel and particular type of engine. For example, a turbocharged petrol engine will have a particular flame temperature. Okay, somebody is unmuted. Please mute. Okay, Raju, meeting you. Yeah. So this Parish's correlation takes care of all of these things. So luckily we have the dissertation on which Parish actually derived this equation. Okay, it was on his PhD dissertation, not as recently as in 2003. So yeah, you must read this dissertation. It is actually provided in the reference link below. Okay, I would like to repeat once again. I know I always say that. Okay, please try to read thesis and dissertation. Okay, and after that the research papers. Okay, don't just look for easy ways to learn on a blog or a video. Okay, a thesis or dissertation is good because it starts from a very basic level with all the introductory thing, and then expands onto the other areas. So please do read them if you want to learn more in depth. Another very important paper is this, a methodology for design of engine cooling systems. Okay, this one is actually a collection. It's like a dictionary. Okay, it has lots of things covered in small area. Okay, you can use it as a reference to go to anywhere. Okay, this is your starting point. Okay, yeah. So moving on. Next one is if we have detailed engine data, what to do then? Okay. So if we have detailed engine data, so what we do is this. Okay. Now at initial it might sound confusing, but yeah, hear me out. So this is a 1D simulation model. Okay, let me use a pen. Yeah. So this is a 1D simulation model. Okay, and it is taking input from a lot of places. Now, some of you will ask, what is a 1D simulation model? Okay, you guys may know about this 3D models. For example, this one is a 3D simulation model for thermal conductivity. It is showing the thermal conductivity of the engine. It is showing the CFD of the entire vehicle. Okay, for a motorcycle, for a car, doesn't make a lot of difference, but yeah, it's showing CFD. So both of these are 3D model, right? We can have a 2D model or a 2D simulation. For example, if we are doing um, the heat transfer simulation or calculation for a flat plate, okay, then it is a 2D problem. Okay, if we are doing a heat transfer problem for a wire, then it's a 1D problem. Okay, those of you, I think anyone in first or second year of engineering, you have solved Fourier's equation, right? In Fourier's equation, you have solved a problem where you solve the problem of heat transfer through a wire. Okay. Yeah. So using the Fourier equation, we can do that. Okay. And yeah, so that's a 1D problem, the heat transfer through a wire. When we first learn the all the formulas of thermal conductivity and all these things, those are all 1D equation, right? The Fourier's law and all. And by using those, we can actually greatly reduce the complexity as well as the calculation time. Okay, as well as the input required to calculate this. Okay, so the 1D simulation is a method of simplifying the system so that we can do quick alterations. Okay. These days we'll have 1D, a connected 1D simulation or a model 1D model of the entire car. Okay, there are some very famous 1D tools. At least those who are in college, MATLAB, right? So MATLAB is a good example of a 1D tool, and you can also do this in MATLAB also. Just MATLAB doesn't have that kind of good built-in features, so yeah, it requires some coding. Okay, but yeah, can be done. So this is a 1D model. Okay, so what it takes is, for example, first we need the heat generated by conversion. Okay, we were seeing this all along. So this is a 1D model, okay, of the engine. Okay, the combustion model. Okay, and it is providing the heat generated by the conversion. Okay, okay. Then we have to consider like how much of heat is being transmitted to the coolant. So that can be done with a like 1D model. Okay, a 3D to 3D like CIE analysis. Okay, like this thermal conductivity analysis. Okay, it can be found out through that way. Okay, we can do 1D CFD for the flow rate. For example, this is a oil engine, so that's why they're considering oil flow rate. But if it's a liquid cooled engine, then we can consider the flow rate for the coolant. Okay, similarly we can consider the flow rate for the airflow in the radiator. Okay. Mm, so all of these inputs, okay, and from different areas, we can take them into our 1D model and create a 1D like solution. Okay, so it's fast. Basically it's fast, that's its advantage. Okay, so there are different 1D CAE tools available. Okay, what I have worked with mostly is for engine. GT Power is quite popular. Most of our OEMs use it. Okay, for cooling circuit, also another tool from GT. GT means Gamma Technologies. Okay, so another tool is GT Cool, very popular. Okay, we have another software called Coolie. It's also quite popular for cooling related calculations. Another software, maybe I think comparatively newer, is Flowmaster. Okay, all of these softwares can do the 1D schematic and calculations. Okay, and next another software is there for converting your 3D to 1D. For example, I have a pipe that is modeled in 3D. Okay, lots of the time we have this, and Now I have to again create the same model for the same pipe. The 1D model for that pipe is just a spreadsheet. Okay, this pipe is this much long, this pipe dia is this much. Okay, it has a thickness of this much, a material of this. Okay, from these things our our the solver, the 1D solver, it will be able to calculate like how much heat, how much friction will it require, okay, to travel this much distance for the coolant, how much pressure drop will occur here, how much heat will be rejected throughout the walls of this pipe. Okay, so these are the 1D solution. Okay, yeah. So moving on. So as you can see here, we have a very simplified 1D model of an engine, or rather it seems simplified from here. Once you expand these things, for example, inside, if you expand this engine block part, you will see an entire like big circuit for this. Okay, same for any other components. Okay, but yeah, this is how a actual 1D model will look like, the schematic. Okay, you can see everything is bypass into pieces, right? One pipe, the bypass valve, the direct bypass the pipe. Okay, we have the connectors. Okay, we have different pipes. This is our radiators. Okay, this is there are two models of the same radiator. One is the showing the coolant side. This is the coolant side, and another is showing the air side. Okay. So the radiator has two kinds of side, thermally speaking, right? In one side coolant enters and leaves, another side air enters and leaves. So in order to get this in a 1D model, we have to create two separate models of the radiator, because thermally they are two separate things. They are linked, but still they are separate. Okay, this is how an actual like real life 1D model looks like. This is a 1D model of a F1 car. uh, Believe it or not, this is a very simple model, or rather the circuit, cooling circuit of an F1 car is a very simple, because they have to save weight. Okay, for example, the F1 one F1 car has only mostly one radiator. Okay, and sometimes then due to new regulations, it will have two radiators, one high temperature, one low temperature, because now F1 cars have batteries and motors. Okay. But yeah, that's all. But uh, the cars that I have worked with, sports cars, they have sometimes 7 8 radiators also. Okay, because we have a very big engines. Okay, lot bigger than the F1 engine, like 4 times 5 times bigger, and we need to cool that engine down. That's for that we need a big radiator. Okay, but on a stylish sports car, we cannot fit a big lorry size radiator anywhere. So we have to split that radiator into small radiators. Okay, we have to position them. Maybe you have seen, there are, on some sports car there are cutout behind the door, right? Now there are strange sized cutouts, or shaped on the front side also. Okay, most of the time you can think that those are for cooling. For example, we have low temperature radiators in front of the vehicle. Okay, okay, and whenever we find some space, we jam a radiator most of the time for high performance cars, because it's difficult, the real estate is very on demand actually. So yeah, uh, the cooling circuit can be quite complex. Okay, at least the circuits that I normally work with are quite complex, with 7 or 8 radiators. Okay, both with normal high temperature circuit plus a low temperature circuit, so quite a complex system. This cooling of an F1 car, you can learn more details about this from this paper. Of course, this paper is also provided in the reference materials. So again, please do fill the feedback form to get access to that. Okay. So yeah, there are some really cool like research papers. For example, this SAE paper, okay, on this whole engine heat balance. So this is these are regarding this what is it called, the heat transfer through 1D. Okay, just give me 1 second. My system is running low on power. Okay, yeah. Really cool papers. Please do read them if you want to get more in-depth knowledge in these areas. All of these are either provided with these. Uh, yeah, uh, these three are provided. These three are attached in the folder. Okay, only this first one isn't attached, so I cannot download this. Okay, so in order to get this, you have to register at JSTOR. So it's an open journal. It will give access to around 100 journals for free per month. Okay, so please do register for it. Okay, now coming to that point, I highly recommend that you register for ResearchGate and MDPI if you are really interested in learning. So these are open journal initiatives, so you can get a access to lots of journals which are otherwise paid. Okay. So these can now be freely accessed. So thanks to these guys. So yeah, moving on. So now we have seen the calculation for the engine. Okay. The next big thing is the calculation for radiator. Okay, but it's a very complex calculation. Okay, some of you guys will find it very difficult. So let's start with the easy one. For example, the fan calculation. Okay. Uh, the limiting factor for the fan design is the tip velocity of the fan. So we have a round fan, right? We have a fan, okay, and it's rotating. Okay. So yeah, it's rotating. This fan is rotating. So at the tip, the velocity will be highest, right? So there is a limit on how fast this tip can be due to noise. If the tip velocity is higher than 110 meter per second, then the noise will be high, noticeable. Okay, so nobody likes a car which makes strange noise. So yeah, that's a quite a requirement. Okay, so yeah, we have to keep the tip velocity under 110 meter per second. So this gives us a limitation on the diameter. Okay, if we make it larger, tip velocity automatically increases, right? If we move it faster, then also tip velocity increases. Okay. So our in ideal condition, what we want is a fan. There are two kinds of fan from their blade profile. Okay. Uh, if I look from this side, for example, this is a fan. It looks from side like this. Okay, and this is another fan. This looks like this. Okay, so this the blade for these fans are just more spread out. Okay, so this kind of fan, I'll call them thin profile, and this one thick profile. Okay, so a thick profile fan is always preferred because in slow it can deliver more air in slow speed. So for example, you can take older ceiling fans, very old ceiling fans, maybe 30-40 years uh, older. Okay, those you see in government buildings. Okay, in our college we used to have them. Okay, so those fans have a very thick profile. So those fans rotate very slowly, but they deliver a lot of air. Okay, but to do this you need more torque, so the motor was bigger. Okay, power consumption is same, but the torque was high. Okay, again for this thin profile, okay, this fan will rotate faster. Okay, and then deliver the same amount of air. Okay, but the thin profile fan will make more noise. Okay, but it will require a smaller size motor because due to the low torque requirement or the lower torque requirement. Okay. So ideally what we want is a thick profile fan. Okay, thick profile fan. Okay, with the largest of dia possible. That's what we want ideally. Okay, but of course there are difficulty. For example, let me just clear out this board. uh, yeah, okay, yeah. So for example, this is our radiator, right? And behind the radiator there will be the fan. So ideally what I want is the fan should be as far away from the radiator as possible. Okay? And the fan should be as thick as possible also. But the issue is space is very limited. So we cannot just make it indefinitely thick. There are other components to be placed also. So there are limitations. So that's why sometimes we have to settle for this 25 to 30 of gap. We cannot do with less than that. So there needs to be some gap between the this radiator, okay, and this fan. Sorry, yeah. So this is the fan. Okay. So if there is no gap, then what we'll do is fan will only suck air from this part, okay, which are like directly attached. Okay. Any coolant here or here won't be cooled because no air is passing through these areas, right? So that's an issue. The further the fan is, the more uniform the pressure distribution will be. Okay. We'll look at them on the radiator part, but yes, the limiting factor for fans are this rotational speed. So with that limiting factor, we back calculate the fan size, okay? And then we match it with the radiator. So yeah, this speed, the tip speed is actually this psi into like the pressure rise of the air, and this like density rise of the air throughout the fan, like before and after situation. Okay, and the psi is a blade shape coefficient, and yes, yeah. So it is different for different blades, and your supplier will provide this information, like which shape coefficient is this current fan. Okay, so you can get this information from a brochure of the supplier. Okay? Sometimes there are two kinds of blades, as you can see on cars. One is straight blade, one is curved blade. So earlier when we used to have steel blades, those were straight, okay, but now we have lots of plastic blades, and those are curved. Blades are always better performing than steel blades. Okay, so yeah, the we can find out our preliminary fan diameter from this. Okay, what it does is basically what is it is doing is ignore the equation. What it is basically doing is volume of air divided by velocity of air. Okay. So it actually gives us the frontal area. Okay, and by using it as a root, we are getting the diameter. Okay. If would have been easier if this thing was square, then it would have been more prevalent. But yeah, if you back calculate it, you can find it like this. Okay, volume by velocity, it gives us the actually um, the frontal area. Okay, also these things have some typical values that we can utilize sometimes. Okay, and also we don't actually have to these academic values. Most of the time suppliers will give us some real data. Okay, and yes, now finally from that the from the diameter, okay, we find the actual angular velocity of the fan. Okay, and then from that angular velocity, okay, we can find out the power that is being consumed by that fan. Yeah, another thing that we can find out is this pressure coefficient and the flow coefficient. So actually fan suppliers, okay, will use these coefficients to identify different kinds of fans. So you have to provide this coefficient data to the suppliers. So this pressure coefficient and the flow coefficient, also there are softwares which take inputs in this terms. Okay. So yeah, these coefficients are important in this regard, that you have to know this coefficient in order to be able to order a fan. Okay, and next up is the pump related calculation. So what we basically need to do for pump is, as you can see, this is the pump. Okay, not going to explore in again, same thing we have already covered. Okay, so this is a kind of pump. It's a simple centrifugal pump. This particular example, this pump is like driven by a separate electric motor. Okay, lots of engine still this day uses a engine driven pump also, nothing wrong with that, that also works fine. But yeah, this electric pump gives us a more flexibility. Okay, so yeah, we need to know how much pressure we need to develop. Okay. For that we need to calculate how much pressure drop we are getting. But yes, as you can see, we need around from 50 to 100 kilopascal of pressure to be generated by the pump. Pump pressure generated is most of the time denoted by this head of water, that is this H. Okay. Okay. Yeah. So there is a consideration of the mechanical efficiency of the pump, and by considering that, we are considering the power consumed by the pump. Okay. If we know the power of the pump, we can go ahead and look at some pumps from the supplier's catalog. Also with from the supplier catalog we can find more details. For example, the characteristic curve of the pump for any centrifugal pump. Okay, there is a characteristic curve, very important. For example, the flow characteristic, the pressure characteristic, how the flow is increasing with the change of rpm or decreasing, how the pressure is changing with the change of rpm. Will need this also to do the analysis. 1D or CFD, whatever you are doing, you'll know, need this data. Okay. So for the total capacity, there is a correlation. It's a simple formula. Okay. We don't actually use it most of the time. The total capacity will come from our benchmark data, like what we were using on the older vehicles. Okay. But yeah, if we don't have anything, then we might take this as a very loose reference. Okay. Then the tank size of the expansion tank. Okay. So as you see on the expansion tank, we have this on the horizontal direction we have maximum system temperature. Okay. On vertical direction we have tank size. Okay. Also again, this tank size, it's not so simple just plotting it from a curve. It's quite a difficult thing to do. Okay. But this can be taken as a loose reference again. Okay. So the maximum temperature attained, for example, is around, maybe in overheating condition, maybe it goes up to 120 degrees centigrade. Okay. So in that case, we are getting around 3% of like excess volume. Okay. So our expansion tank size needs to be like this: 3% of the uh, 3% of the what is it? The entire cooling volume, like this, the total coolant capacity. Okay, so 3% of the coolant capacity. Okay, it will also have additionally some space. Okay, some extra space on top of it. Okay, as you can see, this empty space. So this space. Okay, and sometimes there is also another need for compensating for tilting. For example, take this as the expansion tank. Okay, so you have fuel here. When the vehicle is going through a tight turn, okay, what will happen is this coolant will go in one side, okay, or maybe in another side. Okay. But we need to ensure that this connection with the pipe is not lost, otherwise air will enter. Okay, so for that also we'll have to take some extra coolant. So adding all of this, we get the size of the expansion tank. Okay. Of course, ideally we want to have a like round expansion tank, but it is hard to find that much space. So most of the expansion tanks that we will see will be like a there a tank was there, then it was cut down, okay, to create clearance. For example, here it may be needed 30 clearance with this component. Okay, that's why it was like cutted like this. Similar on other sides also. Inside expansion tank, you can see these are these lines. Okay, these are compartments. Okay, the purpose of this is to prevent the thing that I just said. Okay, this. So if I have compartments like this, okay, now when the vehicle goes through a turn, only the fuels will tilt like this in their own compartment. Right, now the entire tank is not getting empty. So yeah, that's the advantage of compartments. Okay, so going to the radiator calculation, the big thing. Okay, we are also running quite late. So the radiator calculation part, as you can see here, we have a good aluminum radiator. Okay. There are also like radiators in which the header parts are made out of plastic. Those are just cheap, no other advantage uh, by using plastic. Okay. Mm, Maybe another day I'll call someone who is an expert in radiator to give a like talk on radiators. So let me know on the feedback if you want that. Okay, so yeah, as you can see here we have this distribution of uh, mm, like air velocity. So as you can see, this area air is very fast, this area air is not. Okay, it is mainly due to the inlet of the air. Okay, another thing is also due to the suction of the fan. So yeah, these are the things that we have to make sure of. If the fan was small and attached like this, all the air velocity would be like in this area. Okay, there will be no air on the center of the fan because center of the fan doesn't pull anything because of the motor is in the center. Okay, so all of this area would have been stagnant. Only just the area where the fan blades are would have set. So that's why fan calculation is important. Okay. For the preliminary design of the radiator, okay, I'm thinking there is no like using taking everything literally like line by line, but yeah, now we'll take discuss the important things. For example, the heat dissipated by the register, heat to be dissipated by the radiator should be like one like 10% higher than the heat that needs to be dissipated, because there are some losses, okay, in the process. So we need to be able to dissipate more heat. Okay. So also we are assuming that heat that is being dissipated by the coolant to the radiator is equal to the heat that is being taken out by the air, which is a pretty good assumption. Okay, because the heat is not going anywhere else. Okay. Then first we have to calculate the volumetric air flow through the core. This is the radiator core. How much air is passing through there per second or per minute? Okay. What is the volume of air that is passing through? So that's something we have to calculate. So we calculate it based on the vehicle speed. Okay, or maybe in this case it's the flow rate. Okay, this is the vehicle speed. Okay, so this thing will actually come on the other side. Okay, and we are actually calculating this q. Okay, next we need to know the volumetric coolant flow rate. So that's like comparatively easy. Okay. We just have the coolant flow rate data from the pump. Next, we have to calculate the mean coolant flow rate. Okay, someone is unmuted. Okay, yeah, mean coolant temperature. So this is the temperature. Okay, that we need to know. Okay, simply inlet and outlet temperature divided by two. Mean air temperature similarly, inlet plus outlet divided by two. Then we have our required radiator surface area. How much surface area do we need in the entire radiator? Okay, so that is very important because it's the entire heat transfer area. Okay, so in order to calculate that, we have to use the universal uh, what was it, the name, the universal heat transfer coefficient, sorry. Okay, and this is the formula for a cross flow heat exchanger. Okay, and this u seems small, but we have to like explore this u again in detail. So this universal heat transfer coefficient is again a function of like this conductive heat transfer coefficient, convective heat transfer coefficient, like radiative heat transfer coefficient. So considering all of that, we have to consider calculative. Again, this h is a big thing. We have to calculate h. Okay, h will be different for every case. Okay, h is never a constant. Okay. Again, we have this frontal surface area that we need to calculate. Okay, which is the uh, surface area of the radiator front. Okay, and in order to calculate that, what we do is just divide the volume flow rate of air that we saw in the last slide. Okay, where it was this? Yeah, this one. Okay, and we divide it by the velocity, right? And this gives us the frontal area. Okay, from that frontal area, for example, the width. Okay, this one for the width or the height. Okay, we will have one of them as a constraint from the either the styling or the body department, because we'll have to fit the radiator somewhere, right? We'll have mounting and all. So yeah, from that we can take the width, and the height we can automatically then find out. Okay. Of course, yeah, there are methods to calculate the performance of the radiator. Okay, you necessarily don't need them immediately. Okay, even without calculating them, we can design a basic radiator. But yeah, if you want to calculate the performance of the radiator, okay, then it is done based on the ITT, ITD. Okay, that is ITD means inlet temperature difference. Okay, so per inlet temperature difference, for example, if the inlet air temperature is now it is 40 degree, okay, then again it becomes 39 degree, then how much change do I see in cooling? Okay. Is it improving? How much is it improving? That actually shows the performance of the radiator. Okay. So the initial assumption, as you can see, uh, we are actually here seeing the heat rejection per unit of inlet temperature difference, and as you remember, the initial assumption was this: rejected by heat rejected by air equals to heat rejected by coolant. So essentially, we are having a round circle. We have written to the cells. Okay, so this all of this is the function of all of these things. All of the equations that we have seen there is like being covered in this one single thing. So yeah, very important. I want you to look at these things carefully, read those papers, and then only you can figure it all out. I know it is not possible for anyone to understand all of this in this short time. Okay. Okay, yeah, again, I think we have unfortunately ran out of time. Today also, I won't be able to cover the battery thermal management system part. Okay, let us cover this in a its dedicated class. Okay, so yeah, if you guys are still interested in it, let me know. Okay, then we'll have a dedicated separate class for battery thermal management system. Also, we'll cover motor cooling and all. So anything related to electric vehicles, we'll cover. Okay, so now if I quickly move on to the Q&A part. So yeah, this is the time for Q&A. Please ask any kind of questions that you may have. Another thing is there, yeah, you guys can subscribe on YouTube. So these videos will be available on YouTube, although the Q&A part will not be available, but the normal video will be available, so you can take them as reference anytime you want. Okay, so now waiting for your questions. Okay, so yeah, not getting any questions, so I'm guessing yeah, we are good for today. Okay, uh, what I see that yeah, not a very good sign. Okay, not having questions, so yeah, please feel free to connect with me. Okay, or anybody from the upschool team, the mail ID from which you receive the mails. Okay, you can connect through them also, and yeah, I'll be able to uh, get your message. So any kind of doubt, query, please send there. Okay, yeah, so thank you very much everyone for joining. So come in next week for more advanced level things on the schooling system areas also. I hope this will prove to be helpful for everyone. I think there is a question: what tolerance values are considered for the efficiency of these systems? Okay, so uh, we work with a plus minus 5% tolerance. Okay, that is what we aim for while calibrating the 1D simulation models also. So just to clarify what to everyone else. Uh, the 1D simulation models also doesn't give us exactly accurate results. So what we have to do is calibrate them. We have to update or change certain kind of data from the CFD or CE results. Okay, and we do it until we receive a 5% of tolerance margin. Okay, so yeah, there's that. Also, sometimes cooling systems are little bit of overbuilt to cope with some certain scenarios. For example, hot soak scenario. Today we don't have time to explain what hot soak is. Remind me, yeah, next maybe next time we'll cover it. Yeah. Any more questions? Please put it on chat or speak directly. No issues. Which performance data is used in 1D for calibration? Okay. There are different method for 1D. Okay. Yeah. There are different methods for 1D. So 1D calibration. For example, we always used a simple and reliable data for calibration. For example, the kind of data that can be easily uh, um, um, that we can easily get from either CAE or test or both, okay, or CFD, okay, and which is multiple source of validation from that data or those one or two data will calibrate the model. For example, the radiator, we suppose calibrate it with the airflow rate. Okay, so we just add a um, ammeter, okay, on the radiator and run the vehicle. Okay, and then we get an actual airflow rate through the radiator. Okay. Then we get to uh, calibrate the data with that. Okay, sometimes we what we most of the time in the calibration the data needs to be a result. Okay, it cannot be a input data. Okay. For example, the heat rejection through the radiator. Okay. This is something that we can measure from by measuring the temperature and the velocity of the coolant. Okay. What was the inlet temperature of the coolant? Okay. What was the outlet temperature of the coolant? And this is the flow rate. From that, we can measure the heat rejected through the radiator. Okay. And by using that data, we can calibrate the entire model. Okay, and sometimes it works, sometimes it doesn't so well, but yeah, it's a like iterative process. uh, okay, the PPT. Okay, let me check this on real time. Sharing my entire screen. Just a second. Is anybody else facing this issue of downloading the presentation? Okay, okay, yeah, I'm fixing this thing. Please try again maybe in 4 5 minutes. Any more questions? I don't know what is the issue with unmuting. Uh, I have enabled unmuting for everyone. Okay, then, yeah, I'll like to conclude this call. Okay, yeah, I'll figure out this issue. Okay, if there is any, to download the PPT. Thanks, everyone. Okay, again, I have okay, no allowing to. Um, yeah. Okay. We'll have to look into that unmuting issue. But yeah, thanks everyone. I'm sorting this thing about the sharing. Okay. Thanks. Ending the meeting.